This talk is about transferring knowledge in configurable systems using Beetle. My name is Rahul Krishna, and this work was done in collaboration with Vivek Nair, Pooyan Jamshidi, and Tim Menzies. Modern software systems offer exponentially large number of possible configurations. Among these configurations, the key question that we need to answer as developers is what is the best configuration? One approach is to ask other developers, but this is not really practical because the number of options keep growing and most developers ignore almost 80% of the available configuration options. Another alternative is to measure the performance of the software system under various settings. But this is not practical either because it can be too expensive and too time consuming. So if we can't really ask developers and we can't exhaustively measure the performance, what else can we do? An approach to solve this is to reuse previous measurements. And this is called transfer learning. It is known that the act of reusing previous measurement decreases time and cost and minimizes the extent of human intervention. But there is a major unanswered question in this approach. Where do we learn from? Learning from the wrong source for transfer learning can lead to negative transfer, and it can also result in constantly changing or unstable conclusions. So a common practice is to choose the source manually. Again, this becomes increasingly impractical as the number of projects grow. So in order to fully leverage transfer learning, we must select the correct source and we must also automate the process of source selection. And for that, we may use an approach known as bellwethers. Bellwether is basically a leading sheep in a flock with a bell around its neck, and it's used to as an indicator or predictor of something. In this paper, we introduced the bellwether effect and the bellwether method. The bellwether effect states that if a software can be configured and deployed in numerous ways, then there is one deployment among all those deployments with which a model can be built to estimate the performance for the rest. The bellwether method leverages the bellwether effect to find that bellwether deployment and then uses it to find optimal configurations for other deployments. The traditional approach to finding bellwether involves an all pairs comparisons between all available deployments. It's easy to note that this is a polynomial time operation and it has major scalability issues. That is, when M, with number of projects, or the modeling time is extremely large, the approach to find bellwethers becomes significantly slow. In this work, we posit that the discovery of bellwethers can be sped up by using what are known as racing algorithms. Essentially, we sample a small fraction of the configurations from every deployment, and then we use a round-robin approach to eliminate bad sources. And we repeat this process until no other source is eliminated or the budget is exhausted. In the best case, this approach can give us a logarithmic time solution to finding the bellwether project. And in the worst case, it still remains polynomial time. But usually we find that the speed up is somewhere between the logarithmic time and this polynomial time. Now, using the bellwethers for transfer learning is pretty straightforward. All we do is use the racing algorithms I just discussed to discover the bellwether. And once we have the bellwether deployment, we build a machine learning model and use that model to make predictions as to what are the best configurations for all other deployments. Traditional approaches to transfer learning don't use this solution. Instead, they use all available data. And this can lead to poor performance, it can lead to negative transfer, and it can also lead to significant conclusion instability. So in this work, we compare the bellwether approach with numerous non-transfer learning and transfer learning based approaches. More details about these approaches can be found in the paper. In terms of evaluation, we studied 5 subject systems, which were experimented under various workloads, hardware environments, and software versions. Together, the workload, the hardware, and the software versions constitute a single deployment. The goal of this work is to understand if for one deployment, and that is a combination of workload, hardware, and software versions, can we predict an optimum configuration using the other deployments? So in order to evaluate the performance of our approach, we use a metric known as NAR. In essence, NAR computes how close the predicted performance is to the actual optima, and the smaller value, the better. More details can be found in the paper. So in this work, we ask and answer 3 research questions. First, how prevalent bellwethers are. Secondly, how effective bellwethers are compared to traditional methods. And finally, how well do bellwethers perform compared to other transfer learning methods. So for the first research question, we observe that transfer learning with the bellwether has a significantly better performance than transfer learning without the bellwether dataset. And this means that source selection matters. For X264, for example, we found that there are 2 environments whose performance is noticeably better and statistically better than the other deployments in that software system. And this is a trend that we observed in almost all data sets. In every single subject we studied, we noticed that there are a few environments that are significantly better than the other environments. And in essence, bellwethers are very prevalent in the software systems that we studied. The second research question evaluates how effective bellwethers are compared to traditional approaches. To do this, we compare bellwethers with the traditional approach of not transferring anything. And we notice that the bellwether significantly outperforms non-transfer learning methods. And we also notice that we require only 10% of the samples to get the good performance. Bellwethers are in general better than traditional methods. We observe the trend in almost all data sets except for SAC. I'd be happy to discuss the reasons for this offline. The final research question compares bellwethers with other transfer learning approaches. To do this, we compare bellwether with 2 state-of-the-art transfer learning approaches, one being Gaussian process modeling and the other one is logistic regression. And in general, we notice that bellwether outperforms the other methods in 4 out of 5 cases. It seems with SAC, the Gaussian process modeling performs the best. And again, I'd be happy to discuss reasons for this offline. Another point to note is that bellwether used significantly fewer samples to achieve a better performance compared to the other approaches. In this chart shown here, where the y-axis is logarithmic, we note that for each of the data sets that we studied, bellwether required at most 15% of the samples compared to the other transfer learning approaches.
Well, hello again, everyone. Welcome to the Q&A slot for the paper Wins to Learn Transferring Knowledge in Configurable Systems Using Beetle. We have Tim Menzies with us. I'm sure that Tim will be more than happy to take your questions. And we have the first one in here. Well, no, wait. No, sorry. My fault. Come on, guys, far away. This is an excellent opportunity for asking questions to Tim about their nice paper. If there is no question, in the meantime, I will far away first. Okay, let me ask you a question first, Tim. Well, you are an expert in feature models and complex configuration spaces. My question is, is the complexity of the configuration space an issue for this?
So I disagree with you. I'm not an expert in configuration models. I keep running the same heuristic for the last 20 years. Inside a complex problem, there's a simpler one. So about 2005, 2006, I started saying things about keys. There's a small number of variables that set everything else. And all I ever do to my grad students is they come to me with a complex problem. And I say, can you find a way to find those keys in the middle? So you wonder how much of the complexity we think is in our systems is actually we're making it up. We're just not seeing the inherent simplicity. Feature models mapped to CNF are logical formulae. Logical formulae written by people have got repeated structures. Why don't we look to that repeated structure and try to simplify them?
Okay.
Now, if you're asking, have we taken the models in here and done mutation studies where we've increased the complexity, like we've added the constraints and tried to find the breakdown point where, no, we haven't. I used to do that stuff. And then a graph theory person sat down and went and said, the real world is a special case. The real world hides in a tiny corner of the space of possible models.
Okay.
And if you start mutating stuff, you could be you're going to end up on Mars or Jupiter. You're not going to stay on Earth. You know,
well, I was not saying that you should use feature model. I was simply saying that whether the complexity of the configuration space, because you know sometimes the configuration options are mutually exclusive and so on. Whether that can play some kind of role.
Well, I want to do a big shout out to another ICSE paper, not my own. The Boca people that talked, Hongyu Zhang and other people from China, and I've forgotten their names, did a great paper on Wednesday. We've had a lot of success locally with feature models, doing surrogate models with single decision tree. They said, if one tree is good, why not N? And they started doing random forests as their surrogate model. And random forest has some great scalability properties. More importantly, if you put an instance into a random forest, it falls down multiple trees. So you can get a sense not also of the prediction, but also the variance in that prediction. And so one thing we started talking about in the Boca talk was whether we could start talking about non-deterministic systems and sampling across those to find good configuration spaces using some sort of random forest surrogate. So I think it's a very exciting direction.
Okay, thank you very much, Tim. Come on, guys.
But looking at your recent work, I noticed you've got like a horn clause representation for the constraints. And do you find that simplistic?
But this is about your paper, Tim.
I know, but no one's asking a question. I'm completely happy to answer a question about my paper. but consider, our modeling is all based in propositional land, and you do stuff in horn clause land, variables, more expressible. So you might criticize my kind of modeling as being as can't capture certain important entities, which I'm completely open to, by the way. You know, you know.
Not at all. Let me ask you another question, Tim.
Okay.
If I understood well, basically the idea here is optimize performance, right? Maximize performance. What if different configuration options have a different cost? For example, when you migrate something to the cloud, the cost come into play, and the problem becomes a two-objective problem. You want to optimize the performance, minimizing the cost. Right. Will this approach be applicable, Tim?
Yes. We often deal with multi-objective problems in our other work. And if you look at multi-objective reasoning, if you look at our ICSE paper 2013, you know, we were doing 5 objectives for configuration models. Some people are worried about multi-objective reasoning. I say it's a great resource. I say that the more that you can user information you can bring in with goals, the more you can exploit that.
Okay, I see. Okay. Final question, team, from my side, since I see nobody wants is
nobody loves
in. I think that you assume an static workload, right?
Okay.
What if the workload is dynamic? You know, in web systems, for example. What happens in that case? Can you deal with that?
Well, you're asking what's the incremental update time?
Yes.
Now, what's really nice about our stochastic way of selecting operators, you could imagine running it on multiple processors. Like we stochastically do a fight 'em up between the models. So why not turn loose model generator 1 and 20 seconds later on another processor, turn loose model generation 2, and just keep tracking if the two are doing the same conclusions. And if they start disagreeing, I mean, one nice thing about the computational properties about the system we did in here is that it's not killer.
Yeah,
it's not killer. So Now, can we incrementally update the current model? Can we incrementally update the current model? Yeah, I think we could. I think with incremental bellwether, you could start saying someone else is more important, and let's see if their data produces a different conclusion. Yeah, yeah.
Incremental bellwether. That sounds good.
That sounds great, doesn't it?
That's another paper.
Yeah. Okay.
All right, we have 1 minute and a half left. Please remember that at the end of the Q&A, you will see the pop-up with a link that will take you to a specific discussion room for this paper, just in case that you want to discuss something with Tim, although this will be a much better time for doing that.
I fear that I have to not get to that discussion room. My co-author Rahul Krishna should be there in my place. We're
okay.
playing dueling. I love ICSI, but the level of overlap between commitments is getting a little bit crazy.
That must be crazy, especially for you. Yes, I guess. Well, 60
Thank you,
seconds.
Sergio.
Well, let's close the session here. Thank you so much.
Sergio, I really like the Hornclaw stuff that you're doing, and I want to read more about it. I think that's very, very exciting.
Thank you so much, and thank you for the link to the IEEE software. I will definitely read it. Thank you so much.
Yeah, that's some great work from Mike Whalen. I really think that's fantastic.
Great. Well, this is the end of the session. Thank you to all the attendees. Thank you to the speakers. Well, good luck with the rest of the conference. Bye, guys.